Hello, this is Daria, and I'm going to introduce the project that our team has done for the Big Data class. We've used this Goodreads dataset, which is essentially a database of the books from the Goodreads website and the information about them, like the authors and the description, and also the shelves, which is the user book interactions, which user rated which book and how. This is a very big database, so we have found this GitHub repository of 10,000 books from this database. So we've taken this dataset as our essential dataset, but we have used the original big database to add some columns. So here I'm downloading the Big Books database from the Google Drive link provided, and the smaller datasets were loaded using the Databricks file system. Here we can look at the genres of the books, and the format provided in is how many times every book has been added to which genre. So in order to convert it to real genres, I'm expanding this data frame first, and I'm selecting the maximum number of times it was added in every row, and that's how I'm choosing which genre was most popular for this book. And now we have every book in one genre for it. Now we can see the small data set of the books and the large one, the original one. We are going to be using the small one, but as you can see, some of the columns exist in the larger data set but don't exist in the small one. For instance, the description of the book. Because we wanted to do some text mining, I've added this description to our smaller data set. This is the ratings table. And we can see that the small books table is indeed 10,000 rows. So here, the challenge was that in this smaller sample, some of the ID columns were changed, so we had to rename some ID columns in order to match them for joining. So I've taken some of the interesting columns from the larger dataset and joined it to our small books data frame. And I've also added the genres that we've extracted and dropped the duplicates from the resulting data frame. I've also only selected those books that were written in English. So as a result, we're getting 8,700 rows. We can also use this to-read table, which is essentially each user's to-read kind of wish list of books. So we can look at them in order to compare our recommendation results. The books dataset provided had authors separated by commas, so instead I have split them into an array. And also further, we'll need the books and the user columns to have different IDs, and currently they're the same, both of them starting with 1. That's why I've added 100,000 to all the book IDs in order to make them unique from users. And then if we print schema, we can see that some of the number columns are recognized as strings, so we're also converting them to the number columns. And then we're saving our to-read books and ratings tables as users, books, and ratings. And if we read them back in, they're gonna work much faster in Spark than if we continue just working on these data frames. And also, I've written a function that takes the book ID and converts it to the title of the book. We're going to be using it later. And finally, the ratings table had some books and users that were not existent in our books and users tables. That's why I've only joined it on the keys that are existent in our books table. So now our ratings table is slightly smaller.
Hi, today I'm going to talk about data exploration. Let me share my screen. So as you can see here, this data exploration includes both query writing and the visualization. So in the first visualization, we would like to show you like how the ratings are distributed. For this, we are reading the data and grouping by the ratings. So as you can see, average rating versus the user ID. In the next, we are writing a query to show the highest number of reviews by user. So this particular user gave around 200 reviews. In the next step, we are showing the highest rated book. So for this, we are reading the data from the books table and doing and taking the average rating for this particular query. So the complete Calvin and Hobbes book have average rating of 4.882, which is this is the highest one. And in the next query, we are showing the books with the most number of ratings. So for this, we have taken the word ratings count and the average rating from the books table and doing the order by walk rating counts. So these are like as you can see in the result, the Hunger Games is like most number of got most number of ratings and average rating of 4.34. And in the next query, we are showing a number of reviews per book publication year. So over the time period, how number of reviews got varied, we are showing over here. So for this, we have taken the data from books table and doing the by applying the filter, which is like publication year greater than 1900. So as you can see, over the time period, number of reviews got increased, and it was highest in 2011, which is 512, and it got declined after that. In the next query, we are showing average reviews per book publication year. So here you can see like average reviews are like from 4 to 4.1. This got varied. For this, we are reading the data from books table as well and filtering out publication year like greater than 1900 and grouping by the publication year as well. So in the next step, we are gonna show about authors and authors with most number of books. So as you can see, Noro Robots has like highest number of books, which is like 58. For this, we are taking the data from books table and doing the distinct of title by author and grouping by the author as well. So this particular author got highest number of books over here. And in the next step, we are showing the top rated authors. So for this, we are taking the data from the books table and doing the mean of average rating. So for this particular author has highest rating average rating of 4.76. So in the next query, we are showing best books by Stephen King. So we have taken Stephen King as particular author, and we are showing the highest average rating for this for his books. So as you can see, the title Green Mile has got 4.55 of average rating, which is highest among his books. And in the next step, we are showing number of books by year. So for this, we are reading the data from books table and also we have taken the publication year. So as you can see in the 2011, we got like highest number of books, which is like 512.
So for collaborative filtering recommendation system, we use the alternative least squares method that comes with the Spark ML package. And so in ALS, we've turned off the cold start strategy and implicit prefs because that is only applicable when we have hardly no explicit user information. So after that, we create a training and testing dataset and then a hyperparameter list. And because during the ALS iterations, uh, there are matrices are held constants and others are solved using least squares. So we obtain the result of number of models that are tested before we get to the final model is 64, and so process is faster on Spark, so that's not too big of a problem. So after we fit the model and obtain predictions, we find that they are pretty close to the actual ratings. So suppose this user has rated the ID of this book with this ID 3. Our prediction is that the rating will be about 2.5, and we see that here that the root mean square error is 0.83. So that's on average the difference between the user rating and a predicted rating. So we generate recommendations for all the users and we show the top 10. So for user ID 31, the recommended book would be with this ID and this rating, average rating. And so to show this a bit more clearly, we have this function recommend for user that takes in the user ID that we want and outputs the recommended books that would go for that user. So if you put in the ID of user as 1, these are the books that it generates and recommends for that particular user.
Hi, I'm Shraddha and I'm going to explain the content-based filtering. First, we are clustering with respect to book description. Before we start building a model, we have to pre-process our data, for which we are using IDF, which is basically and inverse document frequency. It is used to quantify the words. We'll compute weight for each word in a statement. First step is the tokenizer, which will take a text and convert it into an individual words. Then is a stop word remover, which will remove the redundant word which doesn't contribute to the meaning of the statement. Then is a hash tf, which will convert each word into a vector. Then we are building a model with a number of features is equal to 20. uh, After that, we are using PCA. It is basically a transformation to convert a set of observation. Here we are reducing a number of features from 20 to 5. This will help to in the basically this will convert our data. It will be easier to process in the future in the further techniques. We are using three techniques to get the recommendation. First is k-mean. This is a processed data and we are building a model with k is equal to 20. Here we are evaluating and our silhouette evaluator score is 0.25. So basically this will cluster will give a predicted values with respect to the book IDs in the same cluster. This is where we are getting the values, and this is where we are filtering out the titles. Uh, and these are the final recommendations of the book with respect to this book ID. A second technique is bucketed random projection for Euclidean distance. So here we are using the same process data, and the input is a dense or sparse vector, and each of which represent a point in a Euclidean distance space. The output will be a configurable dimension. So here we are building a model using bucketed random projection, and we are so key here will return the closest point instead of the cluster. So key, with respect to key, we are selecting our book IDs and we are giving a final recommendation with respect to this book ID. Our third technique is latent direct click allocation, which is basically here we are using count vectorizer. This will take the data and return the sparse matrix for each term frequency. We are building our model with k is equal to 20, and these are this is the final transform data. Here when we evaluate, it is the worst of all the three technique. The evaluation score is minus 0.49. Second, we are clustering our data by book features like title, genre, production year, and average rating. Here we are converting our categorical variable and passing it to the assembler and building our model. And with the predicted value, we are predicting the final recommendations with respect to our book ID. Here this is one of the best model because our evaluation score is 0.54, and this is the final list of recommended book with respect to book ID 100001. Our second technique for clustering using the book feature, we are using bucketed random projection. Here we are passing the same features and we are getting the nearest neighbor. This is our list of final recommended book with respect.
This dataset can be approached as a graph because essentially it has nodes as users and books and has edges or relationships between them as the ratings that the users have given to those books. Spark has graph frames library that allows us to use some graph-specific algorithms that we can try in this case. So in order to create the graph, we need to have the vertices and the edges. And vertices or nodes are basically both books and users. So essentially that's why we needed the book IDs to be unique from user IDs. We also have to have all the columns the same. That's why first I'm taking the users table and adding all the books columns and filling them with nulls, and same goes to the book table. And then we're combining the users and the books tables into vertices. For the edges, we're basically just taking our ratings table and we're naming using into source and books into destinations, because Spark's graph frames is a directed graph. So our direction, it goes from the user to the book, how the user rated the book, and the rating is the relationship here. And now we're creating the graph frame and we can use it for our analysis. So this is how the vertices look, just what we've created. And these are our edges, the relationships. Now we can plot this graph and see what it looks like. We're not going to plot all the edges, we're taking 1,000 of them. And what we can see from this graph is that some users tend to rate a lot of books, that's why they're in the middle. But most of the users only rated a few books and they're closer to the books themselves. And green nodes represent users and red nodes represent books. We can do the same thing for just one node, one user or one book. So we're taking user with ID 1 in this case, and we can see which books this user has rated. Now we can do some data frame operations on this graph. And there are a few ways to approach the same problem with graphs. For instance, we can look at the users with the most reviews by just looking at the edges as a data frame and just grouping them by source, which is the user, and just counting that. And we can see the users with the most reviews. We can do the same thing by using out degrees, which also represent the user, and we're getting the same result. The same goes to the most popular books. In this case, we can use the destination of the edges and count them, getting this, and we can use in degrees in order to get the same result here. Graphs can be filtered to create smaller graphs. So these are subgraphs that I've created in this case. And the first one is the new books with the highest ratings. At first I filter vertices in order to include the books that have been published after 2000, and I'm just ordering them by the rating. So these are the new books that have the highest rating. Or we can filter the edges. For instance, here I'm looking for the edges that have rating of 1. And here we're looking for the users who gave the most 1-star ratings. One cool feature that graph frames offer is motif finding, which is essentially using the specific language to look for a pattern in the graph. In this case, I'm looking for a pattern of 3 users giving ratings to the same book, and so that the ratings are the same. So this can be used to also find similarities between users, but it's an expensive algorithm to run, so it's better to use it for some unique cases. Another algorithm provided by graph frames is breadth first search, which essentially looks for the path between a given ID or feature to another given ID or feature of the graph. So in this case, I'm going from the ID number 1 to ID 100,004, and it shows me that it's connected through the edge 5, which is a 5-star rating. The problem in this case is that our dataset is only gonna find those paths if they're directly connected by an edge. It's not gonna find a path between 2 users or 2 books, for example. This is because of the direction of our graph. Users can rate books, but books cannot rate users. This problem is also a reason why we couldn't use the shortest paths algorithm provided, which is also finding the shortest paths between the edges. But again, because our graph is directed from users to books only, we cannot use this algorithm in this case. It would be better for social media analysis, for instance. Label propagation is another algorithm that can help us cluster our books. This algorithm detects communities within a network. The problem with this algorithm is that if you run it for many iterations, it's gonna converge to one big community. So if we run it for less iterations, it's gonna detect more communities. So I've chosen 4 here, and it detected 28 communities. If we look at the communities, we can see that some of them have only 1 or 2 members in there, or books, but some of them have a lot. So this is obviously not a very good clustering algorithm in this case, but we're still looking at it as an example. And I've estimated the silhouette score for this algorithm, and it's actually negative, meaning that the clusters don't really make a lot of sense, which is expected, but we could still see what happens. And because of the negative silhouette score, I have not used it to make any book predictions. Now, PageRank is another algorithm that detects the most popular communities in the graph. So in this case, I've ordered these communities by their rank, and we can see which ones are the most popular ones. Well, I've noticed that these are the same books that are just appearing many times in this data set. So if we do the same thing by grouping the data frame by books and counting them, we can see that the IDs are the same. So basically, this algorithm is just an alternative of finding the most commonly rated books. And we can see from this chart that the most popular books, Hunger Games and Harry Potter, are quite a bit ahead of the other books. Now, another algorithm is power iteration clustering. Basically, it takes a matrix of users and books and the ratings between them as weights, and it reduces the dimensionality and calculates the similarities of the resulting vectors. And it can help us create clusters between the users themselves and not just the books like we did before. And we are getting a negative silhouette score again, but this is all right because this is the one of only the few ways of clustering users in this case, because we don't really have a lot of user features. So if we look at the clusters of the users, we can see that these are what the algorithm came up with. And then we merge these clusters with our main data set. And because these clusters alone are not very useful, we can run a collaborative filtering algorithm by using these clusters instead of user IDs. So if we actually do this and treat clusters as user columns, we can get mean squared error, which is actually very close to the collaborative filtering based on user IDs itself. But in that case, it's been running very slow. In this case, it was faster. And based on this model, we're recommending books to the users and combining them with our data frame. And again, we are recommending for the user number 1. And this is what we've got from this. And these are the books that have been recommended by this model. So the main challenges for us was that a lot of these clustering algorithms were not very useful, and we've mainly used them for the comparison purposes. However, the most useful ones were the collaborative filtering and clustering based on book features. So maybe in future we could somehow combine those two in order to get even better results. We could also look at the books that the users saved to their shelves and treat those as user features and maybe make predictions based on that. So thank you very much.